Hello Slyfox community. In this video we are going to see how to design an OTA or GM in Cadence. First of all, we're going to take a look at the internal circuit of this OTA. This is the schematic of my OTA. In fact, it is a simple differential pair with PMOS active loads and two transistors that are used as source degeneration transistors. I've used NMOS transistors as input pairs, and I've set the width of these transistors to 12 micrometers, and I've set the length to 360 nanometers. Select Q. Here you can see the length and the width. And here I want to mention that I've used TSMC 180 nanometers PDK to design this circuit. These transistors are our source degeneration transistors. Their functionality is so close to a simple resistor. And here I want to say that in my designs, I usually connect the source and bulk of transistors together. Here you can see I've done it for both of them. For source degeneration transistors, I've set the width to 20 micrometers and I've set the length to 360 nanometers. Here you can see them. Width is set to 20 micrometers and length is set to 360 nanometers. And I've connected the gate of both these transistors to a DC voltage of 800 millivolts. You could see the DC voltage is set to 800 millivolts. And this current source is in fact our tail current, and I've set its DC current to 1 milliampere. Here you could see the DC current is set to 1 milliampere. And I've created a pin so that in our designs we can connect this pin here to VSS or ground. Pins for our inputs, and these two PMOS transistors are our active loads and they are configured in current mirror configuration. I've set the width of these transistors to 29 micrometers and the length is set to 360 nanometers, and we should provide the VDD for this node here in our designs. And here is our output, and we can take the output current from this node here. Now we are going to simulate this OTA. First, I've created VDD and VSS. I've set a DC voltage, it is called VDC, and I've set the DC voltage to 1.8 voltage. For 180 nanometers CMOS technology, the VDD used is 1.8 volts. And in order to create VSS node instead of ground node, I've created a DC voltage source with 0 volts. In fact, this node is shorted to ground here. I just wanted to create the VSS node. So I provided the power supply for this OTA, and here is our input. A sinusoidal voltage source is connected to V1. The AC magnitude is set to 1 volts. It is for AC simulation. Its time domain amplitude is set to 1 millivolt, and I've set the frequency to 1 megahertz. This node here is in fact shorted to ground because I have not set any value for this source here. You could see nothing is here. And here is the output, and in order to be able to measure the output voltage, I've placed a 1 picofarad capacitor here. Now we're going to simulate our OTA. Launch ADEL. Now I'm going to choose the analysis. First we perform DC analysis, save DC operating point. Okay, run. Nice. Annotation, DC voltages. As you can see, our output DC voltage is around 900 millivolts. In order to be sure that our OTA is working well, the output voltage must be about VDD divided by 2. Here our VDD is 1.8, and if we divide it by 2, we will reach to number 900 millivolts. And we can see that here we've got a little bit of offset, which is okay for our design. Furthermore, we could tune the width of our transistors to minimize this offset. So our OTA works fine in DC analysis. Now I'm going to perform AC analysis. Frequency 0.01 Hertz to 1 gigahertz. Okay, run. Results, direct plot, AC gain and phase, select, and here is the waveform. First we separate the waveforms. This is our phase. Set the style to solid. Right click, style, solid. I like to see the magnitude first, and as you can see, the gain of our operational transconductor is about 30 decibels, which is acceptable for an OTA which uses degeneration transistors. These degeneration transistors are used to stabilize and linearize our circuit. So the cost of linearization is losing a little bit of gain. And as you can see, the phase in low frequencies is around 0, which is really good. Then I'm going to do a transient simulation. Stop time. We've set the frequency of our input source to 1 megahertz. So I'm going to set the stop time to 10 microseconds. So it is run for 10 periods. And I set the accuracy to moderate. Okay, run. Nice. Results, direct plot, main form, select, and here is our output, and this is our input. Solid. You could see that our output is swinging around 900 millivolts, and here is our input. Let me divide them. You can see that our input is swinging around 0 and its amplitude is about 1 millivolt. It is what we've already set in our simulation. And the output is swinging around 900 millivolts and its amplitude is around 34 millivolts. And our circuit works totally fine. If this content was useful for you, don't forget to give it a thumbs up and subscribe to our YouTube channel for more electronics content. Good luck.